Hi, I'm John Ainsley, CTO at Doulos. In this video I'm going to be talking about easier UVM, sequences. So this video is going to be a tutorial on sequences in UVM. And during that tutorial I'm going to be presenting examples that were constructed using the easier UVM coding guidelines. I'll also be using the easier UVM code generator to generate some example code, and I'll show you how you can do that for yourselves later on using EDA Playground. You can find out all about easier UVM from this URL shown on the slide. So let's take a look at sequences in UVM. So you may be familiar with this diagram from previous videos in this series. The job of sequences in UVM is primarily to generate test stimulus, and sequences, without an R in the name, run on sequencers that have an R in the name. So sequences execute on sequencers, sequences running on sequencers generate transactions. So, as you should already be familiar with, drivers get transactions from sequences running on sequencers, drivers wiggle pins, monitors look at those pin wiggles, assemble the information into further transactions that get sent off to the rest of the verification environment for analysis. And the whole verification environment is partitioned into agents, with one agent for each of the interfaces on the design under test. And then the behaviour of multiple agents can be coordinated or orchestrated by so-called virtual sequences. So virtual sequences typically start multiple sequences running on several different sequencers that are each associated with a different interface on the design under test. So in this tutorial I'll start off by explaining sequences in general, and then we'll look in more detail at virtual sequences later on. So let's take a look at sequences. A sequence is an object of a class where that class extends the base class UVM sequence. UVM sequence is actually parameterized with the type of the sequence item or transaction that the sequence is going to generate. Remembering that a sequence item is a transaction, but if you want to declare a transaction class that can be generated from sequences, you actually have to extend your transaction class from the class UVM sequence item. So in this case we've got a class clock and data default sequence, our user defined sequence class, that extends UVM sequence extended with the transaction type datatx. The sequence class is then registered for factory automation using the macro UVM object utils. It contains a constructor. Like all UVM objects, the constructor has a single argument, which is the string name of the object. And then the thing that's characteristic of a sequence class is that it has a body task. And the body task does whatever it is that the sequence does. And sequences can do a number of different things. Every sequence has a body task, however. The body task will typically generate transactions. A body task can also start other sequences, or if a sequence is generating stimulus for registers in the design under test, then a sequence could simply read and write to registers through the UVM register layer. So technically, a sequence is an object of a class that extends UVM sequence, and it has a body task to do whatever it is the sequence does. And those are pretty much the only technical limitations on sequences. I'll talk more about the use model for sequences as we go through this tutorial. So if we're using a sequence to generate transactions, then the sequence item that we name when we extend the base class is going to be very important. If we're using a sequence to start other sequences or using a sequence to read or write registers, the transaction type is not directly relevant. Because of that, it could even be omitted. Let's take a look at a typical body task for a typical sequence that generates transactions. So this particular sequence just generates a single transaction. Sometimes you do see sequences that generate single transactions. More often, a sequence would generate a number of transactions. But in this case, we'll start off with just a minimal sequence that generates one transaction. So there's 4 essential steps to generating a transaction in a sequence that I've numbered here 1, 2, 3 and 4. So step number 1 is to create the transaction object, and we do that using this coding pattern that we've seen in previous tutorials. Data type, : type ID, : create. Of course, that's known as a factory method in UVM. It's using UVM's factory to create a new transaction object. And note that the name of the system Verilog variable is the same as the name of the string argument to create. That's just good coding practice. The second step is to call start item. And start item notifies the driver that this particular sequence is ready to send a request. Then on return from start item, the sequence randomizes the transaction object, possibly with some inline constraints. We'll see an example of inline constraints later on. If the randomization happens to fail because of some kind of constraint conflict, then we're going to get an error. Then step number 4 is for the sequence to call finish item, and finish item finishes the lifetime of that particular handshake between the sequence and the driver that's pulling down transactions from the sequence. So remember those 4 steps, 1, 2, 3 and 4. Create the transaction, call start item to tell the driver you're ready, randomize the transaction, and then release the transaction to the driver by calling finish item. There is actually an alternative to writing out these 4 steps in full, and that's to make use of one of the macros from the UVM do family. In the easier UVM coding guidelines, we recommend that beginners start out by writing the procedural coding style, that is explicitly calling create, start item, randomize and finish item. But as you become more of an expert, you can save a little typing by making use of the UVM do macro. But be very careful, be wary of using UVM do as a beginner, because you're likely to find that if you make a mistake, the fact that it's a macro may very well hide what's really going on. So here's a sequence that's generating a transaction, and let's complete the picture by looking at the driver that's getting the transaction from the sequence. Here's the run phase method of a driver class, again borrowed from a previous video tutorial in this series. So here in the driver we've got a forever loop, an infinite loop. The driver is calling getNextItem to request the next transaction from the sequence. When the sequence provides the transaction, the driver is calling the doDrive method, which will wiggle pins in the interface to the design under test. And then finally, the driver calls the itemDone method of the sequence item port to tell the sequence that it's done. So there's actually a handshake going on behind the scenes between the sequence running on the sequencer that's generating transactions and the run phase method of the driver that's pulling down transactions. And the next couple of slides just highlight how that handshake works. So here we're talking about the synchronization between the sequence on the left and the driver on the right. So suppose that the sequence starts the ball rolling by calling start item. If the sequence calls start item is then going to block or stall until the driver is ready to get the next transaction. So if we suppose start item is called first, start item will actually block until the driver calls getNextItem. When the driver calls getNextItem, that's the driver telling the sequence that it's ready to start wiggling pins. So at that point, we return from start item and the sequence gets a chance to randomize the transaction just before that transaction is released to the driver. So in quick succession, the sequence returns from start item, calls randomize, and then calls finish item, and it's the call to finish item that releases the transaction to the driver. So when finish item is called, the call to getNextItem on the driver's side returns, and it's then the driver's turn to process that transaction by doing whatever it needs to do, such as wiggling pins on the interface. Finish item is blocked during that time until the driver announces to the sequence that it's finished by calling itemDone. So the driver finishes things off by calling itemDone, and at that point the sequence returns from the blocking method finishItem. We get a very, very slightly different course of events if the driver calls getNextItem first, and we'll look at that next. So suppose the driver starts by calling getNextItem and the sequence isn't ready yet. Well, getNextItem will simply block until the sequence is ready. So getNextItem actually remains blocked until the call to finish item. When the sequence is ready, it will call startItem. StartItem will see that the driver's ready, so it will return immediately. The sequence can then randomise the transaction and call finishItem, and finishItem sends the transaction off to the driver, and then things proceed as they did on the previous slide. Now let's talk about ways we can start a sequence, and there's a number of alternatives to look at. We'll start with the case of starting a sequence from another sequence. So here we're looking at the body task of a parent sequence that is going to start a child sequence. Well, there's quite a lot of code to look at here, so we're going to break it down and look at it step by step. And we'll start off with the simplest case, which I've highlighted here as steps 1 and 2. So at minimum, if a sequence wants to start another sequence, it has a step 1 to create the child sequence object, again by using a factory method call. So it's the type of the child sequence class, type ID create, where we make sure that the string name of the argument matches the variable name. And then at minimum, the parent sequence can go ahead and start that child sequence running by calling its start method. So in step 2 at the bottom, we're calling sequence.start and passing a pair of arguments. The first argument is a reference to the sequencer that we're starting the child sequence on. And the second argument is a reference to the parent sequence, which will always be this. So here we're starting our child sequence on the sequencer mClockDataAgent.mSequencer, and we're making sure to set the parent sequence, the second argument, to the current sequence, whose body method we're executing. So that's the case where we're starting a sequence from another sequence. Typically, however, we're going to want to do more than merely create a sequence and start it running. For one thing, it's really good practice to randomise our child sequence object after we've created it. So better would be a 3-step process. We create the child sequence, randomise the child sequence object in case the child sequence class happened to contain any rand variables, and then start that randomised sequence object on the sequencer. If we're concerned with random stability, we might want to insert yet another step. So a more complete solution is to create our child sequence and then call setItemContext in order to set some context information for that sequence object for the sake of random stability. Generally, random stability is built into UVM in the sense that most objects in UVM get seeded based on the hierarchical path name of the object and the component within the UVM component hierarchy. There's one exception, however, and that is sequence objects. So if you're manually creating and randomizing sequence objects and you're concerned with random stability, it's good to insert this extra step, shown as step 2 here, where before we randomize the sequence object, we're reseeding the sequence object based on the full hierarchical name of the sequencer that it's going to run on. And then finally, if we want the whole enchilada, we can go with 5 steps. So before starting the sequence, we're setting its starting phase. The reason you'll set the starting phase of a sequence is to tell the sequence what UVM phase it's running in, so that the sequence can raise and drop objections to that phase. I'll tell you more about objections in a later video tutorial in this series. So here we have the full works, a 5-step process to starting a sequence from another sequence. Now let's look at starting a sequence from a component, and it's almost identical. If we look at the context here, then instead of this code being inside the body task of a sequence, it's now inside the run phase task of a component, so that's the first difference. And really the only other key difference is that because this sequence is being started from a component rather than another sequence, this sequence doesn't have a parent sequence. So the parent sequence argument is set to null, both in the call to start and also in the call to set context item. Because of the context in which we're starting this child sequence, we also can determine the phase a little differently. Rather than calling get starting phase to determine the phase that we're in, the phase is already available to us as the argument to the run phase method. So we're using the phase argument to the run phase method in the call to set starting phase. But in all other respects, it's the same as starting a sequence from another sequence. Now let's say a few things about virtual sequences. Virtual sequences often cause confusion for beginners, and maybe one of the reasons for that is that some of you might have already seen some OVM, and the treatment of virtual sequences is a little different between OVM and UVM. The term virtual sequence is normally used in UVM to refer to a sequence that happens to sit up outside of the agents in our environment and whose job is to orchestrate the behaviour of the stimulus that's being generated across multiple interfaces to the design under test. So a virtual sequence typically starts sequences running on sequencers within agents, but the virtual sequence itself doesn't run on the agent sequencer, it runs up in some env. There's always been discussion within the UVM community about precisely what the definition of a virtual sequence actually is. The one thing that we can say for sure is that a virtual sequence is a sequence. That is, ultimately it's an object of a class that extends UVM sequence base. Beyond that, it really just becomes a matter of definition. So a good way to think of virtual sequences is to think of a virtual sequence as being a sequence that starts sequences on other sequencers. But really that definition is just a convention and nothing technical about the actual definition of the virtual sequence. Another possible way of characterising virtual sequences is that you could think of a virtual sequence as being a sequence that doesn't generate transactions. And that's very often true, but it doesn't have to be true. In similar veins, suppose you've got a sequence that generates a register test, a sequence that reads and writes registers and nothing else. Well, such a sequence also doesn't generate transactions, so is it a virtual sequence? Well, in the end, this is just a convention. But there's one technical characteristic that really does make a difference, and that is whether or not a sequence generates transactions. And the reason that makes a difference is that if you have a sequence that does not generate transactions, that sequence doesn't actually need to execute on a sequencer. A sequence only absolutely needs to execute on a sequencer if that sequence generates transactions. If the sequence doesn't generate transactions, it's actually optional whether or not that sequence runs on a sequencer. And that's why many experts recommend that virtual sequences, whose job is to start other sequences, themselves don't need to run on a virtual sequencer. I said virtual sequencer. Virtual sequencer is another term that causes lots of confusion, partly because there was a class called virtual sequencer back in the days of OVM. Well, that virtual sequencer class no longer exists in UVM. So just to be clear, UVM does not have a virtual sequence class. UVM does not have a virtual sequencer class. The distinction between a virtual sequence and a regular sequence is really more a question of the role that that sequence is playing. And the term virtual sequence is typically used for sequences whose job is to orchestrate the behaviour of other sequences. So let's look at starting a virtual sequence. And again, the coding pattern is going to be very similar to previous examples that we've seen. So we're creating the virtual sequence object, randomizing the sequence object. And then the additional step is that we're setting some variables within our virtual sequence object to enable the virtual sequence to locate the sequencers that it's going to start child sequences on. So we've actually assigned a couple of variables within our virtual sequence object before we start the sequence running. And then instead of running our virtual sequence on a sequencer, we've run the virtual sequence on the null sequencer. That is, we've passed null as the first argument to the start method. We could have chosen to run our virtual sequence on a sequencer, but we haven't. It's running on the null sequencer. One interesting challenge is how we can access configuration information in a sequence, and that's certainly something that you're going to want to do. So remember, sequences typically generate transactions that represent stimulus, and you may very well want to use the configuration database or use information in the configuration database to parameterize how a sequence executes. Well, it's actually quite straightforward, using the trick of having the sequence pick up the configuration information based on the sequencer on which it's executing. The easier UVM code generator actually makes that very straightforward. So the fragment of code that you can see at the bottom is the code that comes out of the code generator in order to associate configuration objects with particular agents. So in the env, within the build phase method of the env, we're calling config.db set to associate a configuration object with a particular agent. And we're also associating the configuration object with the sequencer within that agent explicitly. This could have been done with a wildcard within the instance string, but instead we've got two separate calls to set. And now here's our sequence. So what our sequence can do is to retrieve the configuration object by fetching the configuration object associated with the sequencer on which the sequence is running, which it can find by calling its getSequencer method. So getSequencer is actually a method of the UVM sequence base class. Any sequence can call getSequencer in order to find the sequencer on which it's currently running. And this sequence is then getting the configuration object associated with that sequencer from the configuration database. Within that configuration object, we've arranged to have a count variable, and the count variable determines how many transactions this particular sequence is going to generate. So we've got a for loop that loops up to a limit determined by the count variable in the configuration object. Each time around the loop, we're creating a new transaction, starting the transaction, and then randomizing the transaction with an inline constraint such that the data value of the transaction is actually the loop count. So here we're going to get a sequence of transactions generated where the data is going up in a descending sequence, starting from 0 and ending up with count -1. Well, you can try this example for yourself by taking advantage of the easier UVM code generator. So let me tell you how to do that. We've actually set this example up on the EDA Playground website at the URL that you can see on this slide here. And the text on this slide is actually showing you the interface template file for this particular example as used by the easier UVM code generator. So you can see here that we have an agent named clock and data. We've got a sequence item where the class name is data_tx, just as you've seen highlighted on the previous slides, and each transaction contains a single random byte of data. The interface then has a clock and data that's connected to the design under test. There's some include files to pull in code fragments defining the behaviour of the driver, the monitor, a coverage collection component, and the sequence that we saw in the previous slides. And then we've also added a variable to the configuration object for this particular agent. Again, exactly as we saw used on the previous slide. So here we've got config var int unsigned count to add that configuration variable to the configuration object for the agent clock and data. Then in the common template file, we've identified the top-level DUT module. We've made a setting nested config objects, and that makes sure that when we generate the configuration objects for each of the agents are going to be nested as references within the top-level configuration object. That just makes things a bit easier to manipulate. We've also added a user-defined code fragment that we prepended to the build phase method of the test, and that user-defined code fragment in this particular test is going to set the value of the count for our particular sequence. So prepended to the build phase method of the test, we've got some user-defined code that grabs the configuration object from the configuration database, and then sets the count value for 4 for the configuration object for our clock and data agent. So with that, I've actually shown you all of the key features that we need to generate the code for this example in EDA Playground. So here's the complete example running. You can see the tabs on the left hand side, which contain both the 2 template files, the common template file and the interface template file for our clock and data agent. Also the pin list file that maps the pins on the DUT, user-defined code fragments, and the code fragment that you happen to see here is the code fragment that's prepended to the build phase method of the test that sets count to 4. We then run our simulation and we can see down at the bottom 5 messages written out from the DUT. The DUT is writing out a message on each clock edge, and it happens because this is a minimal example. The first message is written out on the first clock edge before the DUT actually receives any transactions from the UVM environment. And then with our count set to 4, we can see 4 transactions received with data counting up from 0 to 3. So in this video tutorial, I've introduced UVM sequences, explained the distinction between sequences and virtual sequences, shown you how to generate transactions from sequences, shown you the distinction between starting sequences from other sequences, or from the run phase method of a component, or starting sequences from a virtual sequence. Finally, I've shown you how you can pick up configuration information from a sequence by grabbing the configuration object of the associated sequencer. So at Doulos we deliver training classes, and if you want to know any more about System Verilog, UVM, or any of the topics shown on this slide, do visit our website doulos.com and we'll be pleased to help.